시작해도 될 것 같은데요.
Okay. Good morning, everyone. Today I will introduce a method for key point discovery in behavior videos, and it is achieved by a self-supervised training manner, and it has been published in CVPR 2022. And I will introduce the paper from the following contents. First, I will give you some background information about the behavior videos analysis and the key point estimation, and the issues of the current methods. Next, we will come to the proposed method. The method name is Self-Supervised Keypoint Discovery in Behavior Videos, and I will introduce the paper from the overview and learning formula, and the feature extraction for behavior analysis about this proposed method. And next, I will show you some experiment results. Finally, we will land on the conclusion. Okay, let's come to the introduction about the background information. And when we want to analyze a behavior video, we can see, first I will introduce the behavior video. It is composed of moving agents recorded from stationary cameras, and there has been an increasing effort to automatically estimate poses of agents and classify behavior. And the we can see the first figure shows the current pipeline of the behavior video analysis pipeline. And first, the input is a video of the mouse, and we first use the supervised detector to detect the key point of the mouse, and then we send the detected key points to the downstream models. And for example, the behavior classifiers, and we will get the output that is the behavior labels, predicted behaviors of the input video. However, there are some problems of the current methods. Because we want to get the key point, so we have to train a detector for the input. But it is quite difficult because if we want to train a key point detector, we need the manual annotations. And in this paper, the author want to get an unsupervised discovery key point discovery method. By using the proposed method, when we input behavior video, we can use the unsupervised key point discovery method to find the meaningful key points, and then we will send the predicted key points to the downstream models, and finally we will get the behavior labels. And it should be mentioned that in the downstream model, it is trained in a supervised manner, and it is the downstream task. In this work, we just focus on the key point discovery. And for the key point estimation, it is try to localize a predefined set of key points from visual data. For example, the data can come from the human or the animals, for example, the mouse and the flies. And here, the figure shows the key points detected from the visual data. For example, the first one is the mice, and the right one is the human, and the next is the mice and the jellyfish and the tree. And in this work, our task is to discover the key points from the videos without using any manual annotations during the training phase. As discussed before, the post-estimation models that were developed for behavior videos require human annotations of the defined key points. However, Collecting annotations is time-consuming and labor-intensive, especially for new domains that have not been previously studied. And there are few studies proposed for unsupervised key point discovery task. So in this paper, the author proposed the method for discovering key point on new videos without manual supervision in order to help the behavior analysis on novel settings. So next, we will come to the proposed method, the self-supervised key point discovery in behavior videos. First, I will give you some overview information about the proposed methods. And we aim to discover semantically meaningful key points in behavior videos of diverse organisms without manual supervision. The organisms include the mice, flies, and the human. And when we give a behavior video to the network, we try to reconstruct the regions of motion between a reference frame, IT, and a future frame. And it is accomplished by extracting appearance features from frame IT and the key point locations. We also call it as the geometry features from both the reference frame and the future frame. And we can see here is the overall structure of the proposed method. And the whole network follows an encoder-decoder architecture. We can see there are two inputs for this network. The first one is the reference frame, IT, and the next one is the future frame, IT plus T. And there is an appearance encoder, which has been marked with the yellow, and a post decoder marked with the blue. And there is also a reconstruction decoder marked with the green blocks. And for the reference frame, we're using the appearance decoder and the post decoder try to extract the appearance feature and the geometry features. And for the future frame, IT plus T, we use the appearance decoder and the geometry decoder to extract the geometry features. And we concatenate the geometry features from both the two inputs and the appearance feature from the reference frame. We concatenate the three features, then we send them to the reconstruction decoder. And the reconstruction objective is a spatial temporal difference. And we will calculate a series of losses based on the reconstruction results. And next, we will go deep into the learning formula. We can see, as introduced before, the overall structure are as follows. And for the appearance feature, it is the output of the appearance encoder. And for the geometry feature, it is produced by the post decoder. The post decoder, the output is the heat maps, and there are totally 8 heat maps because we want to detect key points of the input. And then we will conduct the spatial softmax on the heat maps, and we will get the 2D Gaussian maps, which has been shown in the black maps. And then it will represent the geometry features. And for the learning objective is the reconstruction result. And before introducing the final object, we can see here is the final learning object. it is a combination of the different loss functions. And for about the first term is the reconstruction loss. It is calculated by the spatial temporal difference. We can calculate it by using the SSIM measure or absolute difference, or just the simple difference between the input, the reference frame, and the future frame. And we can see the reconstruction loss is the perceptual loss. And the phi here represents the VGG network. And S is the difference between the reference frame and the future frame. And S height represents the reconstructive difference. And here is the reconstruction loss. And about the rotation loss, the loss is proposed for enforced predicted key points has the rotation invariant features. So we calculate it by the L2 distance between, for example, the IR represent, before we calculate the geometry features, we first rotate the input image and we will get the geometry features. And the first one, HG, represents the rotated geometry features, and the input is not rotated, so that we can achieve the rotation invariant. And the next one is the separation loss. The separation loss is introduced for preventing the predicted key points to converge at the center of the image. And P represents the location of the predicted key points. And finally, the final objective is the combination of the reconstruction loss and the rotation equivariance loss and the separation loss. And by using the appearance encoder and the geometry decoder, we can locate the location of the key points. And for the downstream task, for example, the behavior classification, we want to send the extracted features of the geometry information to the classifiers. So we will use the discovered key points from the proposed methods as input to a behavior classifier. And then we will train the behavior classifier in a supervised manner. So except the location of the key point, the UK and VK, we can also calculate the maximum of the heat map. And also we can also calculate the covariance of the input heat map. For the maximum is it can represent the confidence score. It is obtained by choosing the maximum value from the heat map, and the shape information is obtained by computing the covariance matrix from the heat map. So we can get more meaningful information of the heat map by calculating the maximum and the covariance. And we can see the figure has shown the features for the downstream classification task, the input to the downstream classifier. So that's the overall structure and the learning objective of the proposed methods. And next, we will come to the experiment part. And for example, the author evaluates the detected key points on the downstream tasks for behavior classification and post-regressions. And for the behavior classification, the data sets are animal data, and the evaluation matrix is the mean average precision. And we can see The proposed method is a self-supervised method, and the compared methods. The first one is the fully supervised method, and the second one is also a self-supervised method. But we can see for the in the experiment result, the proposed methods can achieve competitive results compared with the fully supervised method. And as introduced before, the proposed methods is designed on the difference reconstruction. And the author also do some experiments based on the image reconstruction. And we can see for the image, if we take the image as the reconstruction object, the performance is quite low. And if we give some information for the image reconstruction based methods, for example, the bounding box location, the performance will achieve a big improvement. But still, the proposed methods has achieved the best performance results. And for the right table, we can see the compared methods is the crafted features based, and the proposed method is using the self-supervised training minor, and it also uses some generic features which can be calculated from the predicted key points location. The features include the speed, acceleration, distance, and the angle. And we can see the proposed method has also achieved competitive results compared with the handcrafted features. And for the next downstream task, it is the post-regression. The post-regression, we use the data. The data comes from the human video, and the evaluation matrix is the mean square error. And we can see for the left one is the left figure table is the results of the post-regression. And we can see the first compared methods is the fully supervised, and the second and the third are self-supervised, but more or less they used some information for the to achieve prior information to achieve good performance. And our proposed methods has achieved competitive results compared with the fully supervised methods. And the right figure has shown some ablation studies of the proposed result. We can see, as introduced before, the image reconstruction means we change the reconstruction object with the image instead of the difference between the reference frame and the future frame. And the second term is the absolute difference. It is about the reconstruction loss. We calculate it using the absolute difference, and the difference is just the low difference between the two input frames. And SSM is the another measurement. It is computed from the comparing the contrast, the luminance, and the structure similarity between the input reference frame and the future frame. And finally, we can see that by using the spatial temporal difference as the learning object, the performance is the best, and the MSE is the lower is better. And we can see with using the SSM, the proposed method has achieved the best performance. And here are also some qualitative results of the proposed methods. We can see there has in the figure we have shown some key points discovered by the proposed method, and we just show the key points discovered with the high confidence values. We can see in the human example, the proposed method can detect the key points of the human. For example, the key points in the leg and the arms and the body. So it is effective to detect the semantically meaningful key points in the videos. And finally, we come to the conclusion. So in this paper, the author proposed a self-supervised method to discover meaningful key points from unlabeled videos for the behavior analysis. And the proposed method is based on reconstruction spatial temporal difference between two frames. It focuses on the key points of the moving agents, and it is general and applicable to behavior analysis across different organisms. Is for example, the human and the mouse and the flies, and it doesn't need any manual annotations. And the experiment results show that the discovered key points are semantically meaningful, and it can help to improve the performance of the behavior classification, and the performance is competitive to the supervised key points methods for the downstream task of behavior classification. So that's the end of my presentation. So is there any questions?
Yeah, let's go back to page 8, slide 8.
Okay.
Okay, so so this is the overall pipeline for performing the learning, right? Or keypoint discovery.
Yeah.
And so it is, the structure is that there is an input, there is a feature generating pipeline for 2 tracks, right? One for appearance and one for key point.
Yeah.
And then outputs are merged toward the reconstruction decoder, right?
Yeah, exactly.
Right. Okay, so the output of the decoder, is that what it says, the prediction? Is that what it is?
The prediction represents the difference between the 2 inputs. It is the absolute difference, absolute abstract of the input to input. We can see in the page 9, the first formulation shows the output.
Right. Okay. So that's the so prediction is that the output of the reconstruction decoder?
Yeah.
Okay.
Exactly.
All right. So what we expect to happen is that within a video, if there are objects that are in motion, right?
Oh, we want to locate the meaningful key points of the video.
Right. So the meaningful key points of a video would be some objects that are making some motion.
Yeah.
Is that right?
Right. Yeah.
Okay. So here in your examples, it seems to be there's only just one object that's in that are moving.
Yeah.
Right.
You're right.
So this is only good for one object per scene. Is that right? Or it doesn't really matter? Can you have like multiple objects making motions and then produce the prediction, which would be the key points?
I think if we put some
because if you go to the experiments, right? Slide 14.
Yeah.
Okay, I see that there are some picture here having like two flies.
Yeah,
so
yeah, yeah.
multiple objects can be also there.
I think it can be also used for two objects. Yeah.
Right, but I guess what I'm saying is that multiple objects of the same class. Can you have like different key points for different objects, different class of objects? For example, one is fly, and one would be like mouse.
In my opinion, I don't think it can generalize to different classes because,
okay, so
yeah.
The key point would be just for one class.
Yeah, I think so.
Per scene, right?
In this paper, I think the author just conduct the experiments on the pure data set. It's not complex.
Okay, so anyway, so when you say, or the paper says key points, it would be just some points that represents the object's position,
yeah.
right? Position,
yeah, the motion.
and so forth.
Is not predefined. If we use the common post estimation methods, we will predefine the key point as for example, the height, the left hand, the right hand. However, in this paper, I think the key points are not predefined. It's just some meaningful key point for the motion.
For the motion, right? Okay.
Yeah.
So how would be able to use, what would be the application of this? If you look around, like, our projects in the lab.
Actually, I think there is a problem for the post estimation. It is very hard to train a post estimation network from scratch because it needs huge data and the computation power. So I think in this paper, it can offer a way to discover the key points without manual annotations, which can help the downstream task, for example, the action recognition.
Right, but again, so that would be only good for in a very confined situation, right? Very restricted situation. Like, for example, you cannot have like multiple class of objects.
Indeed, yeah.
And so forth. I mean, because I think the type of experiments you're showing just contains like very limited number of objects per scene. Like, one person and so forth in the scene. So if you have like if you have a whole crowd or something else happening nearby, if there's a dog, for example, walking, maybe this may not be a good thing. So which means that you still have to do quite a bit of organizing your data set. Just to make it fit for this type of discovery. But I think this is overall still, I think it's a good stepping stone. Okay, thank you.
Okay,
I'm done. My question is done.
Okay. So downstream task is not really something that you consider here then, right? It's mainly for, what was it again? Key points?
In this paper, the author conduct the experiments on the downstream tasks such as behavior classification and the post regression.
Yeah, they did, but that wasn't the focus of the paper here, right?
Yeah, it's not. It focuses on the key point discovery without annotations. Okay. Yeah.
And so I just want to get at least, confirmation that I have at least some sense of following what this is. So on slide 8, if you go back.
Okay.
Slide 8 here, you see 2 frames at time t and time t plus large t.
Yeah.
Had they well, okay, let's stay on here first. So it seems that the network is discouraged to gain anything on the appearance features, but more of a geometry, right?
Yeah.
And so although on the very first layer on the encoder from the reference frame, it pulls out at, let's see, appearance features.
Yeah.
That probably is subtracted out on all the latent features you extract on the downstream. That's how you get everything else blacked out pretty much, right? Only focused on things that move.
The spatial temporal difference is calculated on the original two inputs. Two original inputs is not conducted on the appearance feature.
And so you only have one prediction coming out, right, from the decoder.
From the decoder, if we want to get predict the number of the key point we want to predict, we set it as K. So the post decoder will output K heat map.
That frame that you show on that slide right now.
Yeah, we can see the green.
All the way to the right. Never mind about in between steps, but the output of the decoder, reconstruction decoder, right?
A reconstruction decoder.
Yeah, that's
sorry.
what I'm talking about.
Okay.
And so you only have one prediction coming out that highlights the parts of these two images that moved.
It will, let me show you some. So we can see in the 10, in this figure, it has shown it is an example of the decoder reconstruction. It's the
from the input of the T plus T, right?
It is not just to represent one key point, because we can see the geometry feature represents it is the concatenation of 2D Gaussian centered as the UI and VI, and there are total K. It is a concatenation of the K 2D Gaussian map.
Oh, so you're constructing key points using heat maps.
Yeah.
From the assumption of the 2D Gaussian.
Yeah.
And so you have multiples of these here, right?
Yeah. So
how many channels? Is it fixed? Set numbers or?
I haven't gone deep into in the code, but in I think
it seems to me that it's basically that you need to track, I mean, number of the channels as a number of the key points you want to track or find.
Yeah. Oh, there is a detail. The author in the experiment, the author corrupt the input image to the small patches into the network. So I think
so in this case, I'm still somewhat puzzled how you really teach them to really find the right heat map that corresponds to the key points here. What encourages in terms of training to make that happen?
Let's come to the learning loss function, the final loss function. It is a combination of the reconstruction loss and the rotation loss and the separation loss. And it uses a curriculum learning manner. And it first just use the reconstruction loss to train the network. And once the key points are consistently discovered from the segmented parts of the target instance, it will continue to using the rotation loss and the separation loss. It uses the curriculum learning. And the supervision signal comes from the spatial temporal difference.
How do you even enforce curriculum learning in this case? How do you structure that?
So we can see for the first term, the most important term is the reconstruction loss. Okay. And S represents the difference between the two inputs. And it's showed in
input.
Yeah.
Right.
Yeah, it can be calculated by the original input of the video, two video frames. And the second one, the ice height represents the reconstruction result. The reconstruction is the spatial temporal difference.
Okay, so this is where I'm puzzled. So what's the difference between S and S hat? How do you get the S then? Because right now your network shows S hat, right?
The image below is the S hat, and the up one is the S. S can be calculated by the subtraction of the input, two inputs. It is just
you're assuming then, okay, all right. And so, but what you are getting in the end, right? S of I, for instance, or what you really have is a phi sub S of I, right?
Sorry?
Am I seeing the right notation? Phi, okay. Oh, I see, phi here. So you're only talking about the encoder here, right? Phi, isn't it? That loss comes from only the encoder, phi, not psi, right?
Actually, the perceptual loss here, the phi, is not related to the proposed network.
How's phi constructed then?
So the appearance encoder, it is a ResNet network, and the post decoder, it is originally comes from a post estimation network.
Okay, and so that's what I'm saying. So your loss of the reconstruction loss, you're calculating from the embeddings of the network encoder, right?
Yeah.
Okay, so you calculate that loss, and let's see, still embeddings of IT and I sub T plus T, right? So okay, so the whatever the embeddings, you take the difference, S, right? In L1 loss. Is that how it goes? Spatial temporal difference?
So maybe there are some misunderstanding of the S. We can see in the reconstruction loss, the first term S is the spatial temporal difference. It can be calculated by the subtraction of the input.
Okay. All right, I'm still not quite sure about these loss formulas here, because S is an L1 loss between I sub T plus T minus I sub T, right?
Yeah.
You're inputting that loss into function phi or the encoder phi?
Actually not. The S height we can see here. S height is the output of the reconstruction.
No, never mind about S height. S hat. I'm talking about just S on that term, the left of it, right there.
The S.
Right, that's just the L1 loss.
Yeah.
Right, and then you feed it into phi, right?
It's not loss. is just the pixel subtraction of the input. Two inputs is not loss. S is not loss. It is the supervision signal. Comes from the two inputs.
Okay, this equation then is kind of confusing, isn't it? Because you have a formula for L1 loss right above, right? And that's
this
just
one.
scalar.
This one
if it
is
is a
not.
loss function,
This
it's
one
just
is.
scalar.
This one is not loss. It is just calculated by the original two input image.
And just it's a scalar, right? Single number, L1 norm.
Yeah.
Or is it by term by term?
Term by term. You mean the ice?
No, the first term, spatial temporal difference.
This one.
Yeah. Is that a scalar? Or
I think it is calculated by the pixel by pixel.
Yeah, you have, well, I understand that, but what do you get in the end? Is it a scalar value or a matrix?
Yeah, I think it is a matrix.
Okay, all right. Well, anyway, another thing I was wondering about was if the paper ever mentioned about the sensitivity of their method as how they pick a large T here, right? They didn't really talk about how T was chosen.
Actually, in the experiments, the author has chosen the T as 0.2 seconds.
And is that always pretty much the case for all the animals considered?
The author has conducted the ablation studies about the T, how to choosing T, but in the supplementary. So I didn't show the results of the supplementary in this presentation.
Okay, all right.
Yeah.
Well, I've taken too much time and asking questions simply because I haven't read the paper earlier. It seems that this is working well. Is that what it is in the end?
Yeah, I think so.
Okay. And if you can do it in self-supervised way, and if you can really find some ways of connections to the problems we try to solve, then this can be a good idea that we can try.
Yeah.
Well, thank you. I really enjoyed the presentation.
Okay, I will try it. Thank you. So, any other questions? So if there is no questions, so this is the end of the presentation. Thank you, everyone.
수고했습니다.
수고하셨습니다.